Ancient minds mapped the heavens without a single silicon chip. We are about to journey across millennia and continents to uncover 25 forgotten machines that did exactly that. By the end, you will see the night sky through the eyes of emperors, philosophers, and stargazers who turned stone, water, and bronze into cosmic calculators. How did a device lost in a shipwreck for 2,000 years predict solar eclipses? Why would a civilization build a clock inside a stone elephant? The answers reveal a hidden history of genius written in gears and shadows. What does our own obsession with time say about us? The sea floor off a tiny Greek island held a secret for 2,000 years. In 1901, sponge divers exploring a Roman-era shipwreck brought up a lump of corroded bronze and wood, its purpose completely unknown. For decades, it sat in a museum drawer, a curiosity thought to be a navigational instrument or an astrolabe. But this object, now known as the Antikythera Mechanism, was something far more profound. It was, in essence, the world's first known analog computer. Imagine a device the size of a shoebox encased in wood, with a complex clockwork of at least 30 interlocking bronze gears inside. On its front and back faces, delicate pointers moved across dials inscribed with ancient Greek text, tracking the motions of the sun, the moon, and the 5 planets known to the ancients. This wasn't just a model of the cosmos, it was a calculator for it. By turning a hand crank on the side, an operator could align the gears to any date in the past or future. The device would then display the positions of celestial bodies, predict lunar phases, and even forecast solar and lunar eclipses with startling accuracy. One of its most fascinating functions was tracking the 4-year cycle of the ancient Olympic Games, a reminder that this cosmic computer was also deeply tied to the cultural and social rhythms of Greek life. For a century, the mechanism's true complexity remained locked inside its calcified remains. The breakthrough came with modern imaging technology. High-resolution X-ray tomography and surface imaging allowed researchers to peer through the centuries of corrosion, to read inscriptions worn to invisibility, and to digitally reconstruct the precise arrangement of its gearing. These scans revealed a masterpiece of miniaturization and astronomical understanding. A differential gear, a component not thought to be invented until the 16th century, was right there, working to show the phase of the moon. The Antikythera mechanism stands as a shocking anomaly. It demonstrates a level of technical sophistication that historians believed was impossible for its time, around the 1st century before the Common Era. Its very existence forces us to rewrite a chapter in the history of science. Who built it, for whom, and what other wonders of ancient engineering were lost to the depths of time or the ashes of library fires? This single device, rescued from a shipwreck, proves that the drive to build machines that mirror the heavens is far older and far more advanced than we ever dreamed. The mechanism's discovery shattered a long-held belief that the ancient Greeks were brilliant theorists but poor engineers. They could describe the cosmos with elegant geometry, but could they build a machine to simulate it? The Antikythera mechanism answers with a resounding yes. It stands as physical proof of a lost technological lineage, a bridge between the abstract astronomy of the library and the precise metalworking of the workshop. This forces a haunting question. Was this device a unique masterpiece, a singular flash of genius crafted for a wealthy patron or perhaps a temple? Or was it merely one surviving example from a tradition of building such celestial calculators? The inscriptions on its plates are not unique technical jargon. They use language and conventions found in known astronomical manuals of the time, suggesting the maker was working from established knowledge, not inventing it from scratch. The philosopher Cicero, writing in the 1st century before the Common Era, described a device built by the great Archimedes that sounds eerily similar. He wrote of a globe that showed the motions of the sun, moon, and planets, a device so prized it was carried to Rome as war loot after Archimedes' death. Could the Antikythera mechanism be a descendant of that earlier design? The shipwreck itself offers a clue. The vessel was a Roman cargo ship, likely traveling from the eastern Mediterranean toward Italy. It carried luxury goods, statues, glassware, and this intricate mechanism. This suggests such devices were valuable trade items, perhaps commissioned by the Roman elite who were fascinated by Greek science. If they were being traded, they were likely being produced. So where are all the others? The answer probably lies in the fragility of the materials and the chaos of history. Bronze was often melted down for weapons or coins. Organic materials like wood disintegrate, and the great library of Alexandria with its countless scrolls on engineering burned. The Antikythera mechanism survived only because it was sealed in a cold, dark, anaerobic environment at the bottom of the sea. Its legacy is not a direct line to modern clocks. That knowledge appears to have been lost for over 1,000 years. Instead, its legacy is one of perspective. It rewrites our timeline of human ingenuity. It proves the spark of complex mechanical computation was lit far earlier than we knew. Today, researchers continue to probe its secrets, using the latest three-dimensional scanning and modeling to decipher every tooth on every gear. Teams around the world have built physical and digital replicas, testing theories on how its gearing accounted for the irregular orbits of planets. Each new model brings us closer to hearing the soft click of bronze gears as an ancient user turned the crank, watching the heavens move at their fingertips. This one fragile artifact reminds us that the past is never as simple as we assume. For every mystery solved, a deeper one emerges, waiting in the dark. The sophistication of the Antikythera mechanism was not an isolated phenomenon. In the heart of ancient Athens, a public monument married timekeeping with mythology and civic life. Rising in the Roman Agora is the Tower of the Winds, an elegant octagonal structure of Pentelic marble that has stood for over 2,000 years. While it lacked intricate internal gears, this building was a multifaceted planetary clock in its own right, designed to track the sun, the hours, and even the very winds that shaped Greek voyages and harvests. Each of its 8 sides precisely faces a point of the compass, and each was adorned with a sculpted relief depicting a deity personifying one of the 8 winds recognized by ancient Greek culture. The north side shows Boreas, the cold north wind, bundled in a heavy cloak. On the southwest, Zephyrus is shown as a youthful figure scattering flowers from the folds of his garment. This was not mere decoration. The tower was in essence a massive stone compass and a calendar, aligning the city's daily rhythms with the forces of nature. But its timekeeping functions were brilliantly practical. Carved into the marble walls below each wind deity were vertical sundials. As the sun traveled across the sky, the shadow cast by the tower's cornice would move from one dial to the next, marking the passing hours for any citizen who looked up. This solved a fundamental problem of ancient sundials, which often worked only at specific latitudes or times of year. The Tower of the Winds offered a set of 8 dials, ensuring that at least one would be in the sun during all daylight hours, providing a reliable public time standard. Yet the sun does not shine at night or on cloudy days. To solve this, the tower ingeniously housed a water-powered clock, a clepsydra, inside its base. While the interior mechanism is now lost, historians believe water from a spring on the Acropolis hill above would have flowed into a regulating tank, then steadily drained to drive a mechanism that indicated the hour. This hydraulic system would have kept time flowing regardless of weather or darkness, making the tower a truly 24-hour public clock. Crowning the structure was a bronze weather vane in the form of the sea god Triton, holding a rod that would spin to point directly into the oncoming wind high above the city. A traveler could approach this tower and learn everything they needed to know. They could tell the time by sun or by water, read the direction of the wind and foresee its character from the sculpture, and orient themselves in the city. It was a civic dashboard for an ancient world deeply connected to celestial and atmospheric cycles. The Tower of the Winds represents a different but equally profound ancient approach to tracking planetary movement. Instead of a private, portable computer like the Antikythera device, this was communal infrastructure. It embedded the measurement of time and season directly into the urban landscape, a stone sentinel that made the invisible rhythms of the cosmos visible and usable for every Athenian. Philosophy itself was once measured by the steady drip of water. In the shaded groves of Plato's Academy, where students debated the nature of reality and virtue, time was not kept by the sun's shadow alone. Legend tells of a special clepsydra, a water clock, that Plato himself used to regulate the length of lectures and discussions. This was no ornate public monument. It was a simple, functional device, likely a ceramic vessel with a small hole near its base, filled to a certain mark and allowed to drain. Its purpose was democratic. It gave each speaker in a debate an equal measure of time, their arguments flowing only as long as the water did. Imagine the scene. A student rises to present a case and the vessel is tipped, beginning its steady trickle. His words must be chosen with care, his logic concise, for when the last drop falls, his turn is over. This enforced discipline, turning chaotic debate into a structured pursuit of truth. The choice of a water clock was deeply symbolic. Plato saw the universe as imperfect and changing, a flowing reality. Time, in his philosophy, was the moving image of eternity. What better instrument to measure it than one that embodied constant, irreversible flow? The water clock mirrored the very nature of existence he taught about. It made the abstract passage of time tangible, audible, and fair. While the exact design of Plato's personal clock is lost to history, we know the principle well. Earlier clepsydras in Greek courts were used to time the speeches of lawyers, ensuring no side could talk the day away. Plato adapted this tool of the courtroom for the academy, transforming it from an instrument of law into one of learning. Its gentle, unstoppable drip was a constant reminder. Knowledge, like water, must flow. Ideas must be given their time but not allowed to stagnate, and every debate, no matter how profound, exists within the gentle, relentless current of passing moments. This humble water clock connects us to the human scale of ancient genius. Beyond the grand cosmic computers, sometimes the most profound technology is the one that quietly shapes how we think, talk, and learn together, one drop at a time. Centuries later and a world away, another inventor looked to water and weight to build a clock that was also a spectacle. In the 1200s, in the city of Diyarbakir, the brilliant engineer Ismail Al-Jazari completed his book of knowledge of ingenious mechanical devices. Within its pages was the design for a machine that was equal parts timekeeper, theater, and cultural symbol. The elephant clock. Picture a life-sized model of an elephant, crafted from wood and brass, carrying on its back an elaborate pavilion topped with a phoenix. Inside the elephant's body, a complex system operated in silence. A hidden water tank sat in the howdah, the carriage on the elephant's back. This tank had a small hole in its bottom. As water slowly dripped out over a half-hour period, it lowered a float inside the tank. This falling float was connected by a clever rope and pulley system to a figure seated in the howdah. As the water level dropped, the figure would appear to move, pointing with a rod to marks on a vertical scale that indicated the passing minutes. But the true magic happened on the hour. When the water tank finally emptied, the float would trigger a much more dramatic sequence. A metal ball would drop from the top of the phoenix. It would roll down a channel, landing in the mouth of a serpentine dragon figure mounted on the elephant's tower. The weight of the ball would tip the dragon's head forward. As the head dipped, the ball would roll out, falling with a loud chime into a vase below. At the same moment, the dragon's movement would pull a cord, causing the elephant driver figure to raise and lower his arm, as if striking a drum. Then the ball would be carried by a hidden mechanism back to the top of the phoenix, ready to begin the cycle again on the next hour. This was a fully automated, repeating mechanical show designed to mark the passage of time in a way that was both precise and wondrous to behold. But Al-Jazari's clock was more than a technical marvel. It was a conscious fusion of the known world's great civilizations. The elephant represented India and Africa. The dragon was a motif from Chinese culture. The phoenix drew from ancient Egyptian mythology. The robotic drummer and the water-driven mechanism celebrated the engineering traditions of the Hellenistic Greeks, like the inventor hero of Alexandria. And the overall structure, with its ornate pavilion and precise timekeeping, reflected the scientific achievements of the Islamic world in which Al-Jazari worked. This clock was a physical map of global knowledge, a testament to the interconnected exchange of ideas along the Silk Road. It did not track planets across the sky with gears, but it tracked something equally important. It marked humanity's collective progress, the steady drip of innovation passing from one culture to the next, each hour chimed by a dragon, each cycle a celebration of shared genius. Al-Jazari's book was far more than a catalogue of whimsical toys. It was a detailed engineering manual, complete with assembly instructions and diagrams for 50 devices, from water pumps and fountains to automated musicians and, of course, his clocks. This deliberate act of documentation was revolutionary. In an age where craftsmen often guarded their secrets, Al-Jazari sought to preserve and disseminate knowledge, ensuring these complex designs would not be lost. His elephant clock, described in meticulous detail, stands as a pinnacle of this philosophy. Its timekeeping heart was a marvel of hydraulic engineering. The system relied on a constant, regulated flow of water, not just a simple drain. The secret was in the water tank's design and the use of a float and pulley. As water dripped from a small hole in a submerged bowl, the water level in the larger tank fell at a steady rate. A float attached to a rope would descend with the water. This rope was wound around a pulley connected to the pointing figure on the howdah. The slow, precise descent of the float translated directly into the smooth, pointing motion of the indicator across the time scale. This was a feedback mechanism, a way to transform the messy, variable force of flowing water into a clean, linear measurement of time. But Al-Jazari's genius extended to the heavens as well. Some reconstructions and scholars suggest the clock's pavilion likely featured astrolabic elements or rotating discs that tracked the zodiac or lunar phases. The very structure, with its celestial phoenix and symbolic animals, served as a microcosm, a model of a universe ordered by divine wisdom and measurable by human ingenuity. This synthesis of art, astronomy, and mechanics perfectly reflects the intellectual climate of the Islamic Golden Age. Al-Jazari did not work in a vacuum. He explicitly built upon the pneumatics of the Greek inventors like Hero of Alexandria, whose writings on automata and water devices had been preserved and translated by Arab scholars. The concept of using a float and pulley for measurement had precedence. The elephant motif nods to the cultural and scientific exchanges with India, while the intricate metalworking and geometric patterns showcase Persian artistic traditions. The elephant clock was therefore a physical testament to the transfer of knowledge. It was a node in a vast network where ideas from conquered Greek libraries, Indian numerals, and Persian astronomy converged, were refined, and then expressed in a new, spectacular form. It proved that tracking time was not merely a practical need, but a profound way to demonstrate a civilization's technical mastery and its place in a connected world of learning. While Al-Jazari was documenting his intricate designs on the other side of Asia, an engineering project of staggering scale was already a century old. In the year 1090, during the prosperous Song dynasty, a scholar official named Su Song completed a masterpiece that dwarfed all other timekeepers of its age. This was the water-driven astronomical clock tower, a wooden pagoda soaring 40 feet into the sky, a humming hive of gears, water wheels, and celestial models. It was not merely a clock, it was an entire observatory, planetarium, and public timekeeping station, all powered by the relentless flow of water. Its purpose was to harmonize the earthly empire with the cosmic order, a duty of utmost importance to the Chinese emperor. The heavens were seen as a mirror of the state, and any irregularity in the stars could signal political turmoil. Therefore, tracking planetary movements with perfect accuracy was not just science. It was statecraft. Susong's tower was built to ensure the imperial calendar was flawless, governing everything from tax collection to religious ceremonies. At the heart of this wooden giant was a revolutionary invention, the world's first known escapement mechanism. Picture a massive vertical water wheel, its buckets carefully sized. Water from a constant head tank would drip into the top bucket. Only when the weight of water in that bucket reached an exact amount would it trip a lever, allowing the wheel to rotate forward by one tooth. This catch and release action, this escapement, transformed the continuous energy of flowing water into the precise, tick-tock increments needed to drive a clock. It was the crucial missing piece that allowed for truly accurate mechanical timekeeping, a principle that would not appear in European clocks for another 200 years. This regulated water wheel drove a central shaft connected to an astonishing array of displays. At the top of the tower, an armillary sphere, a skeleton globe of bronze rings, sat under an open roof. This was the observation instrument, its rings aligned with the celestial equator and the path of the sun. But the true wonder was inside, a hollow celestial globe, perhaps 6 feet in diameter, rotated in a dark chamber. Through small holes punched in its bronze surface, the actual stars of the night sky would shine through, their patterns perfectly matched to their positions in real time. As the water wheel ticked forward, this star-spangled sphere turned imperceptibly, completing one full rotation every 24 hours. An observer standing inside this chamber would see the cosmos turning above them, a perfect artificial night sky synchronized with the heavens outside. On the front of the tower, a procession of mannequins emerged from behind doors at each hour, ringing bells and gongs, while tablets displayed the time of day and special celestial events. For decades, this mechanical titan stood in the song capital, its rhythmic clicks and chimes a testament to human ambition. It was a physical declaration that the rhythms of the universe could not only be observed but could be captured, replicated, and put to work in service of an empire. Yet, like so many wonders, its fate was tied to the fortunes of its creators. When the Song dynasty fell to invaders, the great clock tower was dismantled, its knowledge scattered. The escapement, that brilliant heartbeat, was forgotten in the West until it was reinvented centuries later. Susong's tower reminds us that progress is not a straight line, but a river with many channels, some of which run dry for ages before being rediscovered. The ambition to capture the cosmos was not born in libraries or palaces alone. Sometimes it was forged in bronze and held in the hands of a tribal priest. Deep in the forested hills of what is now Germany, a discovery was made that pushed the origins of European astronomy back by 1,000 years. Found by treasure hunters in 1999, the Nebra sky disk is a stunning bronze disk about the size of a dinner plate, inlaid with gold symbols that shimmer against a blue-green patina. Dated to around 1600 before the Common Era, this is the oldest known realistic depiction of the night sky anywhere in the world. It is not a clock with gears, but it is a timeless calendar, a portable observatory that turned the heavens into a tool for survival. At first glance, the gold symbols seem abstract, a large circle and a crescent, clearly the sun and moon. A cluster of 7 dots, almost certainly the Pleiades star cluster, a key marker in ancient skies worldwide. But the most intriguing additions are 2 golden arcs along the rim, added later. These arcs precisely mark the angle between the summer and winter solstice sunsets at the site's latitude. Another later addition, a curved band along the bottom, is often interpreted as a solar barge, a mythological boat carrying the sun through the underworld at night. This was not a child's drawing of the sky. It was a sophisticated instrument. Hold the disc upright, align it with the landscape, and you have a working model. The position of the Pleiades near the crescent moon, as shown on the disc, signaled a specific time in the early spring. This was the signal to begin the year's planting. The solstice arcs provided the calendar's fixed points, the longest and shortest days that structured the ritual and agricultural year. In a society without writing, this bronze disc encoded the essential knowledge needed to maintain the community. It told them when to sow, when to harvest, and when to perform the ceremonies that kept their world in balance with the cosmic order. The disc was likely used in concert with a specific horizon, like the nearby Mittelberg Hill. A priest or elder would hold it aloft, comparing the gold symbols to the actual sky and landscape behind them, reading the time of year as clearly as we read numbers on a dial. Its value was immense. It was found buried with 2 precious swords, axes, and bracelets, a hoard fit for a king or a high priest. The Nebra sky disk shatters the old notion of prehistoric Europe as a dark, isolated place. Its design shows an understanding of astronomical cycles that required generations of observation. The gold itself came from Cornwall in Britain, the bronze from the Alps. This object is proof of far-reaching trade networks and the sharing of high-status knowledge across the continent. It represents a different kind of timekeeping, one rooted in ceremony and the land, where tracking the planets and stars was quite literally a matter of life and death. The Nebra sky disk was a farmer's almanac cast in bronze, but in the jungles of Mesoamerica, an entire civilization built its identity around a calendar of breathtaking complexity. For the Maya, time was not a line to be measured, but a sacred, living force that moved in grand, interlocking cycles. Their cosmic clock had no gears of bronze, but it was engineered with mathematical precision, its mechanisms written in codices and carved into the stones of towering pyramids. At its heart were 2 primary cycles that meshed like celestial gears. The first was the Tzolk'in, a 260-day sacred round. This was not based on any obvious astronomical cycle like a year or lunar month. Instead, it was created by combining 13 numbers with 20 named days, generating a unique 260-day sequence before it reset. Each day carried a specific spiritual energy, an omen that guided everything from naming a child to declaring war. Running parallel was the Hob, a 365-day solar year divided into 18 months of 20 days each, plus a short, unlucky period of 5 days at the end. These 2 cycles, the sacred Tzolk'in and the practical Hob, turned independently. Think of them as 2 enormous spinning wheels. One wheel has 260 teeth, the other 365. A specific day is defined by where the teeth of both wheels align. How long would it take for a particular combination of a Tzolk'in day and a Hob date to repeat? The answer is 18,980 days, roughly 52 solar years. This period was known as the calendar round, and its completion was a moment of profound terror and renewal for the Maya, a time when they feared the world might end if the gods were not properly appeased with ceremony and sacrifice. But the Maya looked even deeper into time. To track longer historical and prophetic cycles, they used the long count. This was a linear count of days from a mythical starting point, which scholars correlate to August 11, 3114 before the Common Era in our calendar. The long count allowed them to inscribe dates on monuments with absolute specificity, recording the reigns of kings and the anniversaries of cosmic events over millions of years. This system was not abstract, it was a practical tool for statecraft and astronomy. Maya priests were obsessed with the planet Venus, which they associated with war and the god Cayahuil. They calculated its synodic period, the time it takes to reappear in the same place in the sky, as 584 days, an accuracy within mere hours of the modern value. In the Dresden Codex, one of the few surviving Maya books, detailed Venus tables allowed priests to predict its appearances as the morning and evening star for centuries into the future. These predictions dictated the timing of warfare. Raids were launched not when the army was strongest, but when Venus rose in a specific phase, its light seen as a divine mandate for battle. The architecture itself was part of this clock. At the Pyramid of Kukulkan at Chichen Itza during the equinoxes, the setting sun casts a shadow of undulating triangles down the northern staircase, creating the illusion of a massive serpent descending to Earth. This was a public, stone-calibrated marker of the solar year, a moment when the building itself told the people the time for planting or ceremony had arrived. The Maya did not see themselves as moving through time. They saw sacred time moving through them, its cycles of birth, sacrifice, and renewal dictating the fate of kings and cornfields alike. Their calendar was a vast intellectual engine designed to synchronize human activity with the relentless, divine mathematics of the cosmos. Stonehenge stands silent on the Salisbury Plain, a ring of giants frozen mid-dance. For centuries, its purpose was a perfect mystery, seen as a temple, a burial ground, or a druid circle. But look closer, and the stones begin to speak a language of light and shadow, aligned not to earthly kings but to the sun and moon. This Neolithic monument, built in stages starting around 5,000 years ago, may be the most ancient and imposing planetary clock we have ever built. Its massive sarsen stones, some weighing over 25 tons, were dragged from quarries miles away and erected with a precision that suggests far more than ritual. They form a calendar in stone, marking the extreme boundaries of the solar year with breathtaking drama. At dawn on the summer solstice, the longest day of the year, the sun rises directly over the outlying heel stone. From the center of the circle, an observer would see the first golden sliver of sunlight appear precisely in the narrow gap between the uprights of the largest trilithon, a massive 3-stone archway. This alignment is not an accident. It is a deliberate, engineered sightline, a celestial gun sight targeting the sun's northernmost rising point. 6 months later, at the winter solstice, the phenomenon reverses. The setting sun would have framed itself perfectly between the uprights of another trilithon, marking the sun's southernmost retreat and the year's shortest day. These are not subtle markers, they are monumental, public, and undeniable, turning the very architecture into a giant timepiece that announces the turning of the seasons to an entire community. Yet the sun may only be part of the story. The outer ring of the monument, a circle of 56 so-called Aubrey holes named for their 17th century discoverer, hints at a more complex function. These pits, now filled, once held wooden posts or perhaps stones. Intriguingly, the number 56 is a key figure in tracking the moon's complex cycle. A lunar eclipse only happens when the sun, earth, and moon are perfectly aligned, and this alignment recurs in a pattern known as the Saros cycle, which lasts about 18 years and 11 days. Scholars like Gerald Hawkins propose that by moving markers around this circle of 56 holes, 1 hole per year, ancient astronomers could have predicted these terrifying events. After one complete circuit of 56 years, the marker would be close to predicting 3 Saros cycles, allowing them to forecast when the moon would turn an ominous blood red. Imagine the power this knowledge granted. In a world ruled by celestial omens, the ability to stand before your people and announce that the moon would be consumed on a specific night was not just science. It was a form of divine authority, a demonstration of control over the very heavens. Stonehenge, therefore, might have been a dual-purpose machine. Its grand stones tracked the steady, reliable pulse of the solar year, governing agriculture and ceremony. Its hidden circle of holes may have tracked the more ominous, unpredictable rhythm of lunar eclipses, allowing priests to transform fear into awe. It was a clock that ticked in both annual harvests and generational cycles, a permanent stone ledger for a civilization that wrote its most important knowledge not on parchment but on the landscape itself. High on the windswept plains of Wyoming, a different kind of stone circle holds its secrets. The Big Horn Medicine Wheel is not built of towering monoliths, but of carefully placed limestone rocks laid out on a remote mountain ridge over 10,000 feet in the air. At first glance from above, it looks like a giant wagon wheel roughly 80 feet across. A central cairn, a pile of stones, serves as its hub. From this hub, 28 spokes radiate outward to a surrounding stone ring. And around that ring, 6 more smaller cairns are positioned at irregular intervals. This is not a random pattern. It is a star map etched into the earth, a calendar aligned to the horizon that guided the lives of the Plains Indians for centuries, perhaps even millennia. The central cairn is the anchor point, the observer's station. From this spot, the world aligns. On the morning of the summer solstice, an observer standing at this central hub would see the sun rise directly over one of the outer cairns. As the day progresses and the sun arcs across the vast sky, it would eventually set in alignment with another cairn directly opposite. These 2 stone markers act like giant sighting pins, framing the sun's longest journey across the sky. But the wheel tracks more than just the sun. The other cairns point to the rising positions of 3 brilliant stars crucial to the seasonal cycle. One cairn aligns with the heliacal rising of Aldebaran, the red eye of the constellation Taurus. Another points to Rigel, the bright blue foot of Orion. A third targets the brightest star of all, Sirius. In the ancient world, the first appearance of these stars just before dawn, after a period of being invisible, signaled specific times of year. The rising of Sirius, for instance, often coincided with the hottest days of summer. For a people living in harmony with the land, these celestial events were not just pretty lights. They were urgent memos from the universe. The alignment of Aldebaran might signal the time to begin the buffalo hunt as herds moved to new grazing grounds. The appearance of Rigel could warn of the coming winter, a sign to finalize preparations. The medicine wheel wove these astronomical cues into a single, durable instrument. The 28 spokes likely hold significance too, possibly relating to the lunar cycle or serving as a counting tool for rituals. This high-altitude observatory was a place of profound ceremony and teaching. Elders would bring initiates here, using the silent stone alignments to pass down knowledge of the stars, the seasons, and the sacred stories that connected the people to the cosmos. It was a classroom without walls, where the curriculum was written in stone and light. Unlike the static monuments of Europe, the medicine wheel feels organic, a part of the landscape it measures. It doesn't impose order on the sky, but instead finds order within it, using humble rocks to create a permanent, communal memory of the turning heavens. Deep in the Yucatan jungle, a stone tower rises in a shape utterly alien to the surrounding Maya pyramids. The caracol, named for its spiral staircase, looks less like a temple and more like a modern observatory, a round dome perched on a broad platform. This architectural oddity was a precision instrument, its narrow windows cut like rifle sights to target specific moments in the sky. While other structures marked the sun, the caracol was dedicated to the treacherous dance of Venus. For the Maya, Venus was not a beautiful evening star. It was a god of war, its appearances and disappearances dictating the timing of raids and royal ceremonies. The tower's designers engineered its windows and alignments to capture these critical events. One narrow slit, for example, frames the northernmost setting point of Venus, the farthest west the planet ever travels in its 8-year cycle. Another aligns with the sunset on the spring equinox. From a specific chamber inside, a priest astronomer could watch the light of the setting sun or the gleam of Venus slide perfectly along a stone corridor, a celestial confirmation that the time was right. This was not passive observation, it was active calibration. The Maya kept meticulous tables predicting Venus's 584-day cycle. But the sky could be cloudy, the tables copied over generations could develop errors. The caracol served as a stone reset button. When Venus was predicted to reach a key position, the priest would ascend the tower. If the planet shone exactly through the designated slit, the calendar was confirmed. If it was off by even a sliver, the complex calculations would be adjusted. This physical verification ensured their cosmic clock remained in perfect sync with the actual god of war moving overhead. The consequences of this precision were earthly and brutal. The Dresden Codex, a Maya book of astronomy, contains warnings. Certain phases of Venus were auspicious for launching attacks, while others promised certain defeat. A king would not march his army based on a hunch. He would wait for the word from the caracol's observers, for the moment when the stone instrument confirmed the heavens had ordained victory. This round tower transformed abstract calculations into a matter of state security, its silent alignments whispering the exact moments to spill blood in the name of the stars. The caracol's windows framed the gods of war, but another civilization found its celestial calendar in the silent play of light and shadow on a canyon wall. High on Fajada, but in New Mexico's Choco Canyon, the Ancestral Puebloans engineered a solar marker of breathtaking elegance and fragility. Behind three massive, leaning sandstone slabs, they carved two spiral petroglyphs into the cliff face. For most of the year, these spirals sit in shadow, but on the summer solstice, something miraculous happens. As the sun climbs to its highest point in the sky, a sliver of sunlight slips between the giant slabs. This beam, sharp as a blade, pierces the center of the larger spiral with a dagger of light. For 17 minutes, the sun dagger bisects the carving perfectly, a moment of celestial alignment so precise it feels like a message. As the days shorten toward the winter solstice, the dagger of light appears lower, touching the smaller spiral, marking the sun's retreat. This was no accident of erosion. The slabs, each weighing several tons, were deliberately positioned. The Ancestral Puebloans, master astronomers and builders of the great houses in the canyon below, moved these colossal stones to create a natural observatory. The spirals themselves are not just targets. Many scholars believe they represent the sun's journey, or perhaps the great cosmic cycles of migration and return central to Puebloan cosmology. The sun dagger transformed an abstract solar event into a visible, dramatic spectacle. It turned a sheer cliff into a communal calendar, signaling the time for planting, for ceremony, for the entire community's rhythm. Its discovery in the 1970s revealed the depth of astronomical knowledge in this ancient culture, knowledge passed down without written records, encoded instead in stone and light. Yet this wonder is heartbreakingly fragile. The very act of studying the sun dagger has threatened its existence. Foot traffic on the butt shifted the delicate slabs, a change of mere millimeters. Today, the alignment is damaged, the perfect dagger of light now distorted. The site is now closed to the public, a sacred clock that can no longer be wound, its precise timekeeping lost to protect what remains. It stands as a powerful reminder that these ancient technologies are not just feats of engineering, but delicate dialogues between culture and cosmos, conversations we must listen to with great care, lest our own footsteps silence them forever. The silent desert sun demanded its own precise measure. Among the treasures of ancient Egypt is a deceptively simple instrument, a limestone slab now known as the Cairo calendar sundial. Dating back over 3,000 years, possibly to the reign of the great pharaoh Thutmose III, this device reveals how the Egyptians partitioned their day with elegant geometry. Its design is a stark T-shape. A long base bar inscribed with a series of curved lines supports a perpendicular crossbar raised at one end. To use it, the sundial was oriented with the base pointing east-west. As the sun traveled from morning to afternoon, the shadow cast by the raised crossbar would sweep across the base, but this was no simple straight line. The inscribed curves on the base are hyperbolas, carefully calculated so that the tip of the moving shadow would touch each curve at a specific, equal division of the daylight hours. The Egyptians divided their daytime into 12 seasonal hours, meaning the length of an hour changed with the seasons, longer in summer and shorter in winter. These curves on the Cairo sundial automatically compensated for that change, providing a flexible, accurate measure of time throughout the year. This portable stone clock was deeply tied to a much grander celestial system. The Egyptians told time at night by observing the rise of 36 star groups called decans. Each decan would rise just before dawn for a period of 10 days, marking a 10-day week in their civil calendar. Over the course of a night, the successive rising of these decans would partition the darkness, creating a stellar clock. The Cairo sundial was the solar counterpart to this nocturnal star watch. Together, they created a continuous cycle of timekeeping, linking the rhythm of daily labor and ritual to the eternal procession of the sun and stars. This was timekeeping woven into the fabric of existence. The precise hours dictated the schedules for temple offerings, the times for prayers to Ra the sun god, and the organization of work on monumental projects. In a civilization where the pharaoh was the living embodiment of cosmic order, maintaining the correct time was a sacred duty, a way to keep the universe itself running smoothly. This humble T-shaped stone is a testament to that profound belief, a tool that transformed the moving shadow of a crossbar into a dialogue with the divine. The sun dagger carved its calendar into a cliff, but in the heart of Rome, an emperor carved his mastery of time into the city itself. Following his conquest of Egypt, Emperor Augustus ordered a spectacular public timepiece, the Horologium Augusti, or Solarium of Augustus. At its center stood a towering red granite obelisk, a war trophy taken from Heliopolis, the ancient Egyptian city of the sun. This 100-foot monolith was more than a symbol of victory. It was the gnomon, the pointer, of the largest sundial the ancient world had ever seen. Its shadow fell across a vast marble pavement in the Campus Martius, a plaza inlaid with a grid of bronze lines and Greek inscriptions. This was not merely a clock to tell the hour. It was a cosmic map and a political declaration in stone and shadow. As the sun moved through the year, the obelisk's shadow swept across the pavement, its tip touching specific lines that marked not only the hours of the day but also the passing days of the year and the 12 signs of the zodiac. On the autumn equinox, the shadow would point directly toward the nearby Ara passes, the altar of peace, a monument celebrating the peace Augustus had brought to Rome. This alignment was no coincidence. It was a choreographed spectacle designed to link the emperor irrevocably with the cosmic order. Every citizen who watched that creeping shadow saw a daily demonstration that Augustus, like the sun itself, governed the rhythms of their world. The obelisk, a sacred Egyptian object now serving a Roman purpose, visually declared that Rome had absorbed the ancient knowledge of conquered lands and now commanded time itself. The Horologium transformed the abstract passage of days into a public theater of power, proving that the greatest clocks are never just about time, they are about who controls its narrative. The emperor's obelisk cast a shadow for the entire city, but timekeeping could also be a deeply personal affair. In the libraries and on the caravan routes of the Byzantine Empire, a new kind of instrument emerged, one that fit in the palm of your hand yet contained multitudes. These were portable sundials, masterpieces of miniature engineering carved from ivory or cast in bronze, their surfaces a dense forest of engraved lines, curves, and tiny holes. Far more than simple time tellers, they were compact cosmic computers for the educated elite, blending Greek science, Roman practicality, and the spiritual needs of a changing world. A typical example might be a small ivory leaf, hinged like a book. Opening it reveals a stunning complexity. Multiple sundial types are engraved on the inner surfaces, each with its own tiny, adjustable gnomon. One dial might be a simple horizontal sundial for general use. Another could be a polar dial with hour lines fanning out from a central point, designed for more accurate reading at specific times of day. But the true genius lies in their adaptability. Many of these dials feature a string nonum, a tiny hole through which a thread with a bead would be passed. By adjusting the bead's height according to a latitude scale inscribed on the device, a traveler could precisely calibrate the sundial for their location, whether they were in Alexandria, Constantinople, or a distant trading post. This personalization made the instrument accurate across the vast expanse of the empire. For a scholar, it was a tool for study and prayer. For a merchant on the Silk Road, it was a vital piece of navigational and scheduling equipment. But some of these devices held an even more specific spiritual function. As the Byzantine world transformed, later portable sundials began to incorporate a feature essential for Muslim worship, the Qibla indicator. A small compass or a diagram of the winds would be engraved alongside the timekeeping scales. By aligning the sundial with the sun to find local noon, a traveler could then use the compass to determine the correct direction to face for prayers toward Mecca. This single object, therefore, became a nexus of knowledge. It embodied the preserved Greek and Roman science of mnemonics, the practical need for portable time in a connected world, and the devotional requirements of a new faith. It was a clock, a calendar, and a compass, all etched onto a surface no larger than a modern smartphone, a silent witness to an age where science, commerce, and spirituality traveled together in a scholar's pocket. The pocket sundial calibrated a traveler's day, but one ruler's ambition demanded instruments of monumental scale. In the early 1700s, Maharaja Jai Singh II of Jaipur looked at the brass astrolabes and small quadrants of his time and found them wanting. He believed their small size led to observational errors, tiny mistakes that multiplied in the celestial calculations used for calendars and navigation. His solution was an act of architectural audacity. He would build observatories where the instruments themselves were buildings, vast constructions of stone and marble so large their scales could be read to an accuracy of just a few seconds of arc. The result was a series of 5 Janta Mantas, with the largest and most complete standing in the pink city of Jaipur. This is not a collection of telescopes, but an open-air laboratory of colossal geometry, a place where shadow and substance merge to measure the heavens. Dominating the complex is the Samrat Yantra, the supreme instrument. It is a right-angled triangle of masonry, its hypotenuse, the gnomon, soaring 88 feet into the sky, angled precisely to match the latitude of Jaipur. On either side of this giant wedge stretch 2 colossal quadrants, curved marble scales built at ground level. As the sun moves, the shadow of the gnomon sweeps across these quadrants. But this is no ordinary sundial. The scale is so immense, each marble marking represents just 2 seconds of time. A trained observer could literally watch the shadow creep, telling the local solar time with an accuracy unmatched by any portable instrument of the age. The Samrat Yantra was the heartbeat of the observatory, its steady shadow setting the standard for all other measurements. Nearby stands the Ram Yantra, a pair of complementary structures designed to measure the altitude and azimuth of celestial bodies, essentially their precise position in the sky. Each consists of a circular pit with a central pillar surrounded by high walls. The walls and the floor are inscribed with a grid of lines. To take a measurement, an observer would stand in the pit, sighting a star or planet along the top of the central pillar and the opposite rim. The point where this line of sight intersected the grid on the wall gave a direct angular reading. The genius is in the pairing, 2 identical structures aligned north-south, allowing measurements to be taken for any object in the entire sky without any blind spots. It turned the simple act of looking up into a precise geometric coordinate. Perhaps the most conceptually beautiful instrument is the Jai Prakash, or light of Jai. It consists of 2 complementary hemispherical bowls sunk into the ground, each a mirror image map of the celestial sphere. Across their concave surfaces, marble crosswires are strung, marking the celestial equator, the ecliptic, and other coordinates. A small metal ring is suspended at the center of each hemisphere. During the day, a tiny patch of sunlight passing through this ring would project onto the marble map below, pinpointing the sun's location among the stars. At night, an observer could move inside the structure, aligning their eye with the central ring and the crosswires to plot the position of a star. The Jai Prakash made the entire sky tangible, a dome you could literally step into and navigate from within. These monumental instruments were not built for show. They were tools for a massive scientific project. For years, teams of astronomers used them day and night, compiling fresh observational data. The shadows on the Samrat Yantra, the alignments in the Ram Yantra, the pinpoint of light in the Jai Prakash all fed into the creation of the Zij-i-Muhammad Shahi, a set of astronomical tables far more accurate than anything previously available in the region. These tables predicted eclipses, planetary positions, and the movements of the stars, refining calendars and aiding navigation. Jai Singh stone giants were a bold declaration that to understand the cosmos, sometimes you must build on its own colossal scale, using sunlight and shadow to write your equations in marble across the earth. While Jai Singh was building his stone giants, another monumental observatory had already been watching the stars for nearly a century. In the heart of 17th century Persia, under the reign of Shah Abbas the Great, a different kind of celestial workshop rose in the city of Isfahan. Led by the polymath Sheikh Bahai, this observatory was a center of gravity for the finest astronomers, mathematicians, and instrument makers of the Safavid Empire. Its primary tool was a masterpiece of precision, a mural quadrant so immense it was built directly into the observatory's foundation. This was not a portable device, but a permanent part of the architecture, a stone and brass eye trained on the meridian. Imagine a quarter-circle arc, its radius stretching many feet across the floor and up the wall, meticulously calibrated with degree and minute markings. At its center point, a fixed sighting apparatus allowed an observer to track a star as it crossed the local meridian, the imaginary north-south line in the sky. The star's altitude at that precise moment, read off the giant scale, gave a critical data point for mapping the heavens. This massive quadrant provided the measurements for the observatory's grand project, the compilation of the Zij-i-Sultan star tables. These tables were far more than a list of star positions. They were a comprehensive computational system, a database that allowed astronomers to calculate planetary positions, predict eclipses, and determine the exact times for sunrise, sunset, and prayer throughout the year. The Zij-i-Sultan was intended to surpass all previous Islamic astronomical tables, a testament to the Safavid court's ambition to be a leader not just in political power but in scientific knowledge. This work was urgent. Accurate timekeeping was essential for the Islamic calendar, which is based on lunar months. Citing the new crescent moon to mark the beginning of months like Ramadan required precise knowledge of the moon's path. The observatory's data helped resolve disputes and standardize time across the empire, weaving scientific authority into the fabric of daily faith and ritual. Beyond the mosque, the tables were vital for navigation across the vast trade networks of the Silk Road and the Persian Gulf. A merchant or captain with access to the Zij-i-Sultan could better chart a course under the stars, turning celestial mechanics into commercial advantage. The Isfahan Observatory thrived in a rare climate of intellectual patronage. Shah Abbas gathered artists, scientists, and philosophers, creating a vibrant cross-pollination of ideas where poetry, architecture, and astronomy were seen as interconnected expressions of divine order. Sheikh Bahai himself embodied this fusion, renowned as a mystic, a mathematician, and an engineer credited with designing Isfahan's ingenious water distribution system. In this environment, the observatory was more than a research facility. It was a symbol of a civilization peering deeply into creation to find both practical utility and spiritual wonder. Yet, like so many centers of learning, its glory was fragile, dependent on the favor of a single ruler and the shifting tides of history. Sealed within a cave for nearly 1,000 years, a scroll of paper survived to become the oldest complete star map in human history. This is the Dunhuang Star Chart, a breathtaking manuscript from China's Tang Dynasty, created around the year 700. To unroll it is to open a window onto the night sky as it appeared over the Silk Road more than 13 centuries ago. Painted in brilliant red, black, and white inks on fine paper, the chart is a masterpiece of observational astronomy. It meticulously plots the positions of more than 1,300 stars, grouped into 257 distinct Chinese constellations. The sky is presented in two revolutionary formats. One section shows the circumpolar stars, those that never set, radiating out from the North Star in concentric circles. The other section is a series of 12 rectangular sky maps, each covering about 30 degrees of celestial longitude, depicting the band of stars that rise and set throughout the year. This combination of polar and equatorial projections demonstrates a sophisticated, systematic approach to mapping the entire visible heavens, but this was not merely a scientific catalogue. Each constellation carries a name and meaning drawn from the rich tapestry of Chinese mythology and state ideology. Here is the purple forbidden enclosure, the celestial mirror of the emperor's palace. There, the white tiger of the west and the azure dragon of the east, cosmic animals governing the seasons and directions. Astronomers who were imperial officials would have used this chart as a reference to track the movements of planets and guest stars, what we now call comets or nova, against this fixed stellar background. Their observations were critical for timekeeping, for updating the imperial calendar, and for the all-important practice of divination. Any unusual celestial event was seen as a message from heaven concerning the emperor's virtue and the state's future, making this star chart both a scientific tool and a political instrument of immense power. Its survival is a story of pure chance. In the early 20th century, a Taoist monk named Wang Yuanlu discovered a hidden library, Cave 17 at the Mogao Grottoes near Dunhuang, sealed since the 11th century. The cave was a time capsule packed with tens of thousands of manuscripts, paintings, and textiles. Among this treasure trove was the star chart, likely stored for safekeeping. Its discovery rewrote the history of astronomy, proving that detailed graphical star mapping flourished in China centuries before similar works appeared in Europe. This single scroll, preserved by dry desert air and forgotten by time, connects us directly to the eyes of Tang Dynasty stargazers who saw not just points of light, but a celestial empire written across the dark. High on a sacred ridge at Machu Picchu, a single granite pillar rises from a carved stone platform. This is the Intihuatana, the hitching post of the sun. To the Inca, it was far more than a sundial. It was a spiritual anchor point, a device designed to literally hold the sun in place at its weakest moment. The pillar, carved from the living bedrock of the mountain, is a masterpiece of precise stonework, its angles and facets aligned with the cardinal directions. Its primary function was to mark the solstices, the critical turning points of the solar year. During the winter solstice in June, the sun in the southern hemisphere is at its lowest, weakest point. The Inca feared it might continue to flee, leaving them in perpetual cold and darkness. On that day, priests and the emperor himself would perform a solemn ceremony. As the sun reached its zenith, the pillar would cast no shadow at all, the stone appearing to merge with the light. This was the moment the sun was hitched, secured to the earth for another year. Conversely, during the summer solstice in December, the pillar's shadow would fall at its shortest, marking the sun's peak strength. These were not subtle observations. They were public, dramatic confirmations of cosmic order, witnessed by the elite in the citadel. The Intihuatana directly linked the emperor, the Sopa Inca, to the sun god Inti. By presiding over this celestial binding, the emperor demonstrated his divine role as the mediator between the people and the life-giving sun. His authority was not just political, it was cosmological, proven annually by the silent testimony of stone and shadow. This astronomical precision had a deeply practical purpose, regulating the entire agricultural calendar that sustained the empire. The solstice markers told farmers exactly when to prepare the soil, when to plant potatoes and maize, and when to harvest. The stone clock in the sky governed the rhythm of life for millions. Similar Intihuatana stones existed at other major Inca sites, each one calibrating the local calendar to its specific latitude and horizon. They formed a network of sacred observatories, synchronizing the rituals and labors of a vast mountainous empire with the unwavering cycle of the sun. To destroy one was to attack the very order of the world, which is why Spanish conquerors systematically sought to topple them, attempting to sever the link between the people and their celestial sovereign. The one at Machu Picchu survived only because the city itself was forgotten, its stone pillar left waiting for the sun's return, a silent witness to an empire that measured its destiny by the length of a shadow. While stone pillars and water wheels tracked time in real space, another civilization perfected the art of recording it for the future. Across 7 centuries, from the reign of King Nebuchadnezzar II to the conquests of Alexander the Great, Babylonian scribes performed a nightly vigil. Their instrument was not a geared wheel or a stone alignment, but a stylus and a wet clay tablet. Night after night, generation after generation, they inscribed what we now call the astronomical diaries, creating the longest continuous scientific dataset in human history. These were not stories or myths, but stark, meticulous logs. A typical entry might read, Month 6, night of the 15th, sunset to moonset, 8 degrees. Jupiter was in front of the swallow. A lunar eclipse occurred and was total. They recorded everything: the moon's daily path against the stars, the first and last visibility of planets, the dates of solstices and equinoxes, and every eclipse. They even noted correlating weather and key economic data, like river levels and grain prices, searching for patterns that linked heaven and earth. This relentless, bureaucratic documentation created something revolutionary: a predictive database. After centuries of data piled up in temple archives, patterns became undeniable. The Babylonians discovered, for instance, that lunar eclipses recur in a cycle of about 18 years, the Saros cycle. They learned the precise rhythms of Venus and Jupiter. With this deep historical record, they could not only describe the past but forecast the future, predicting celestial events with remarkable accuracy. This empirical foundation allowed them to move beyond simple observation into the realm of mathematical astronomy. They developed complex arithmetical schemes, step functions that could model and predict the varying speeds of the moon and planets. Their genius was in their pragmatism. They sought mathematical rules that worked, even if they didn't always understand the physical why behind them. This vast celestial database also fueled another powerful endeavor: horoscopy. The same data used to predict an eclipse was used to cast a personal horoscope. The belief was straightforward: if the motions of celestial bodies influenced rivers and harvests, surely they influenced human destiny. A child's fate could be read in the planetary positions logged at their birth, positions pulled from the same meticulous diaries that tracked the moon. In this way, the humble clay tablet became the ultimate clock. It didn't just measure hours, it archived cycles. It transformed the fleeting moment of a star's appearance into a permanent data point, a piece of a puzzle that, when assembled over generations, revealed the very mechanics of the cosmos. The Babylonian scribes, in their diligent nightly work, built the foundational code for understanding time itself, not with gears of bronze, but with the patient, permanent press of cuneiform into clay. In the bustling agora of a Greek city, time was not told by a single shadow, but by a public stone covered in holes. This was the parapegma, a communal almanac carved in marble, where astronomy met the practical needs of every farmer, sailor, and merchant. Unlike a sundial that marked the hours, the parapegma charted the entire year, its surface inscribed with the names of days, months, and crucial astronomical events. The true genius was in its interactive design. A series of small holes were drilled next to each daily or weekly entry. A citizen, likely a designated official, would move a wooden peg from hole to hole each day, providing a clear, physical marker of the current date within the grand cycle of the year. But this peg-board calendar did far more than count days. Its inscriptions were a digest of celestial wisdom. They noted the heliacal rising of specific bright stars, the moment a star first becomes visible in the dawn sky after a period of invisibility. The appearance of the star Arcturus in September, for example, signaled the coming of autumn storms for sailors. The morning rising of the Pleiades cluster in may mark the start of the safe sailing season and the time for harvesting grain. Each peg moved was a step in a dance choreographed by the stars, linking the abstract motions of the cosmos directly to the rhythms of survival. These stone almanacs also recorded weather lore and seasonal markers, predicting the likely onset of rains, winds, or heat based on generations of observation. For a farmer, consulting the parapegma told him not just the date but whether to sow or reap. For a ship owner, it dictated when to launch his vessels and when to keep them safely in harbor. It was a shared database of environmental knowledge, etched in stone for the entire community, ensuring that the vital lessons of the sky were never lost. The parapegma democratized time. You did not need to be a priest or an astronomer to understand its message. The moving peg and the simple inscriptions made the complex clockwork of the heavens accessible to all, turning celestial cycles into a trusted guide for daily life. This public stone stood as a testament to a society that saw no divide between the science of the stars and the necessity of the harvest, where tracking a star's rise was as practical as checking the weather. The patient scribes of Babylon tracked time with clay, but on a remote island in the Pacific, another culture carved its calendar from the earth itself. The massive stone moai of Easter Island are famous for their haunting faces, but their backs tell a different story. These giants do not stand alone. They are mounted on long, ceremonial platforms called ahu. Recent surveys suggest these ahu are not randomly oriented. Many are precisely positioned so that when you stand at a central point on the platform during a solstice, you witness the sun rising or setting directly between two distant, specially chosen moai that flank the vista. This transforms the statues from solitary sentinels into a vast, open-air sighting device. The ahu platform becomes the observer's station, the distant moai become the foresights, and the rising solstice sun becomes the confirming event. In a society utterly dependent on the cycles of nature for fishing and farming, marking the solstices with such monumental permanence would have been essential. It tied the power of the ancestors embodied in the moai directly to the life-giving rhythm of the sun, turning the entire coastline into a sacred chronometer. Across the world, another forest of stones whispers of a similar ambition. On the coast of Brittany, France, the Karnak alignments stretch for miles, a staggering grid of over 3,000 upright megaliths arranged in parallel rows. Walking among them is like moving through a petrified army, a geometric puzzle set in the landscape. Unlike the solar focus of Easter Island, the leading hypothesis for Karnak involves the moon. Certain key sightlines through the alignments appear to target the extreme rising and setting points of the moon during its 18.6-year cycle, known as the lunar standstill. When the moon reaches these northernmost and southernmost points, it seems to pause before reversing course, a slow, dramatic celestial event. The Karnak stones may have been placed to frame these lunar extremes, using the natural horizon and specific outlier stones as markers. This would create a colossal calendar not for days but for generations, predicting tides, seasons, and perhaps even scheduling long-term ritual gatherings. Both the Moai platforms and the Karnak rows represent a monumental approach to timekeeping. They did not measure hours but epochs. They encoded critical astronomical knowledge directly into the landscape, building calendars so vast that to read them, you had to stand in the very world they measured. Stone and shadow gave way to gears and gilt in the soaring naves of Europe's great cathedrals. Here, in the heart of the medieval world, the ancient drive to map the heavens found a new, spectacular home in monumental public clocks. These were not mere timekeepers, they were theological statements in brass and iron, designed to show humanity its humble place within the divine cosmic order. The astronomical clock in Prague's Old Town Hall, built in the early 1500s, is a masterpiece of layered time. Its face is a dizzying array of concentric dials and golden hands. One ring shows the 24 hours in Old Czech time, where the day was counted from sunset. Another tracks the Babylonian hours, which varied in length with the seasons. A third displays sidereal time, the measure of Earth's rotation relative to the distant stars, not the sun. Above it all, animated figures of the apostles parade past windows each hour, while a skeleton representing death tolls a bell, a stark reminder of time's ultimate limit. This clock synthesized ancient timekeeping systems into a single, public spectacle, a bridge between the old cosmic views and the new mechanical age. In the choir of England's Wells Cathedral, a clock built around the same time presents a different vision of the medieval universe. Its great, colorful face depicts a geocentric cosmos, with Earth fixed at the center and the Sun, a golden fleur-de-lis, orbiting around it. Every quarter hour, a thrilling automated performance unfolds. Figures of mounted knights joust in a circle above the dial, while a seated character known as Jack Blandiver kicks his heels to strike 2 bells with hammers and 2 more with his heels. This charming theater served a serious purpose. The joust represented the constant struggle between good and evil in a world governed by celestial motion. The clock made the philosophical architecture of the medieval mind visible and tangible, turning abstract cosmology into a moral and mechanical play for the gathered worshippers. But perhaps the most ambitious of all was the Strasbourg Cathedral clock, a project that evolved over centuries into a Renaissance wonder. Its complex face includes a perpetual calendar calculating religious feast days, a planetary dial showing the positions of the sun and moon, and a magnificent astrolabe. Its crowning glory is a procession of automata. Every day at solar noon, figures of the 12 apostles march before a figure of Christ, while a crowing rooster, a symbol of Peter's denial, flaps its wings and calls. Lower down, a mesmerizing celestial globe rotates, showing the phases of the moon and eclipses. This clock was a cathedral within a cathedral, a microcosm of a universe believed to be meticulously ordered by God. It continued the ancient tradition seen in Su Song's tower or Al-Jazari's elephant, using mechanical genius to manifest cosmic harmony, now filtered through the lens of Christian theology. These cathedral clocks were the final, glorious chapter of an era. They stood at the crossroads, using the new technology of weight-driven escapements to perpetuate the oldest human quest, to see the turning of the heavens reflected in the turning of a gear, and to find our fleeting moment within eternity's grand design. A single idea echoes across these stones and gears, a thread of knowledge woven through time and desert, jungle and cathedral. The water escapement that gave heartbeat to Su Song's tower in 11th century China, the float and pulley that animated Al-Jazari's elephant in 12th century Anatolia, the differential gear that modeled the moon's phases in the 1st century Antikythera Mechanism, these are not mere coincidences. They are distant peaks of the same mountain range, evidence of a shared human ingenuity rising to meet a shared celestial puzzle. civilizations separated by continents and centuries arrived at eerily similar solutions because they were asking the same profound questions of the same silent sky. The flow of water, the geometry of shadow, the mathematics of cycles, these became the universal languages for a dialogue with the cosmos. This parallel invention reveals something fundamental. When humans look up, we are compelled not just to wonder but to build, to make the abstract movement of planets tangible, to hold time in our hands, whether in carved stone or polished bronze. Yet alongside this independent spark, there was also a deliberate and precious exchange. The Silk Road was more than a path for spices and silk, it was a conduit for constellations. Along those dusty trails traveled not only merchants but ideas. Greek astronomical texts saved from the ashes of Alexandria were translated into Arabic in Baghdad's House of Wisdom. Centuries later, those same texts, now enriched with Persian and Indian observations, made their way into Latin Europe. The design for an astrolabe, perfected in the Islamic world, became essential for medieval European sailors and monks. The concept of the clockwork automaton, seen in Hero of Alexandria's writings, inspired the courtly wonders of Byzantium and later the animated figures of European cathedral clocks. This was a slow, centuries-long relay race where the baton of celestial knowledge was passed from hand to hand, culture to culture, each adding its own layer of refinement. A Babylonian arithmetic scheme might influence a Greek geometric model, which would later inform an Indian sign table, all eventually converging in a single instrument. The portable sundials of the Byzantine traveler, with their adjustable string gnomon and Qibla indicators, are perfect emblems of this fusion, containing Greek science, Roman practicality, and Islamic devotion in one palm-sized object. This thread connects the Nebra sky disk's local solstice markers to the global ambition of Jai Singh's stone observatories. It links the Maya priest tracking Venus for war to the Babylonian scribe logging Jupiter for omens. They were all participating in the same grand human project to find our place in the turning machine of the universe. To measure time by the cosmos is to seek anchor points in eternity. It is a declaration that our fleeting lives, our harvests and empires are part of a pattern vaster than ourselves. Whether to predict a flood, schedule a prayer, legitimize a king, or simply to know when to plant, this drive transcends any single culture. It is a foundational human trait as innate as storytelling. From the first person who scratched a line to mark a shadow's reach to the teams programming satellite navigation today, we have always been clockmakers. Our materials evolved from granite to silicon, our power source from dripping water to orbiting atomic vibrations, but the essential quest remains. We are still building mirrors for the heavens, trying to catch the reflection of our own brief, brilliant moment in the endless celestial dance. This journey across 25 ancient devices reveals a stunning panorama of human genius. We have seen cosmic clocks built from every material imaginable, from the delicate bronze gears of a sunken Greek computer to the living granite of an Inca sun hitching post. Some were driven by the steady drip of water, others by the patient sweep of a shadow, and still others by the silent, eternal alignment of stone with a star's first light. Each was a response to the same celestial puzzle, yet each was shaped by the unique culture that gave it life. These were never just instruments for telling the hour. They were profound expressions of philosophy, power, and a deep, unshakable desire to find our place in the grand scheme of things. For the Maya, a tower's window was a divine command for war. For the Chinese emperor, a towering water-driven planetarium was proof of his mandate from heaven. For the Babylonian scribe, a clay tablet was a sacred record of cosmic order. They built these marvels to predict harvests and eclipses, to schedule prayers and raids, to legitimize kings and to appease gods. In doing so, they left behind a legacy far greater than timekeeping itself. They left us a map of the human mind, charting our relentless quest to bring the infinite heavens down to a scale we could touch, measure, and understand. That quest did not end with these ancient wonders. It simply changed form. The gears are now microscopic, the power source atomic, but the essential drive remains. We are still building mirrors for the cosmos, trying to see our own reflection in the stars. So tell us, which of these ancient clocks captured your imagination the most? Was it the intricate mystery of the Antikythera Mechanism, the monumental ambition of Jai Singh Stone Observatory, or the silent communal wisdom of the sun dagger? Let us know in the comments, and if you enjoyed this journey into the mechanics of history, be sure to subscribe. There are countless more mysteries waiting, each with its own story etched in time.